heard of Swift. The purpose of this is to get a little bit closer to a hands-on tutorial. What we've done is we've delivered several tutorials for in-person audiences where we have pretty good control over the test equipment and things like that. What we're trying to branch out to is to put some test facilities out in the cloud so that anybody can try Swift on some initial distributed nodes and then gradually migrate toward increasingly powerful parallel resources that you have available on the campus. By the way, I'm getting a little bit of squealing in my earphones here. I don't know, Marco, is my mic too high or?
No, I hear it.
Okay, I'll just continue and ignore that for the moment. Okay, so at any rate, one of the notable parts about Swift is that it can send work to a variety of resources. So we'll try to get a glimpse of that in this tutorial here. So this is kind of the general context and you know that it's architected for, and as I think you probably know, that the whole purpose of Swift is basically to orchestrate the execution of ordinary application programs, sort of in a high throughput manner where jobs are schedulable by their data dependencies. So I'm going to try to spend most of my time on screen here and just go back to slides in a few places. To the tutorial that we're trying to prepare for you is at this URL. So you may want to get a browser over to there. I apologize that this this online material is still has a few kinks as we adjust it to the dynamic environment and to the latest changes on UC3. So this URL will be updated, and we'll try to get word out to this, I guess, through the CIC email lists when various revisions of this are more ready for you to try. But I think you can actually go to this URL, and it should have enough material to actually follow along for the beginning parts of this. So what's out there at that URL is a tutorial that basically walks you through several introductory examples just to learn the Swift language. So these first 6 parts are done on a on any login host or laptop, you know, most preferably a Linux or a Mac laptop, and then these exercises here are at the moment these are set up for UC3, and these are set up for cloud. So I'm not sure how many people out there have access to UC3. We'll be redoing this at the CIC workshop at Duke in a couple of weeks, and there will, I think, all the participants will have access to a campus grid-like facility called OSG Connect that's based on the architecture that was devised with UC3. Okay, so tutorial starts by fetching it from SVN. So here's a place to download all the material. I think one of the issues here is that because we had transformed this from a regular machine, we didn't give you instructions for downloading Swift, but you can actually go to the Swift website. So that's at swift-lang.org. And if you go to the download page here, then this download button will get you a tarball, which is exactly the Swift that we're going to be running in the tutorial. So I'm actually logged into UC3, and we'll just sort of follow along from there. I'm running this latest release candidate of a point release of our 094 system. And so you can just test Swift sanity with Swift-version. And it's run best with a Java, it's like an Oracle-based Java of like 1.6, preferably 1.7 or later. Okay. And the tutorial what you get in the tutorial directory is like a setup script. So you basically source setup.sh. We'll provide a version for C shell flavor users in a revision pretty soon. And I've already done this, which has given me Swift in my path, and it's given me a little global config file in a global directory, which looks something like this, that sets a few properties about how Swift should operate in terms of file retention and error retry and staging techniques and things like that. But notably here, as we run Swift, Swift uses 2 files in addition to the Swift scripts. One file tells Swift where the execution sites are that it can use, and the other file says where apps are located on those sites. So we'll take a look at those later. So just as the first first example is part 01. I'm not going to go through all these. I'll just sort of give you a flavor of it. What you'll see in each of these examples is a Swift script. This is a very trivial one. Okay, and you run it just by saying Swift p1.swift, and it's basically going to use the local application list and sites file based on the global parameters that we had set up here. So these you set typically once for most of your Swift work and seldom come back to it. And then when you're working in a local application script, you can typically just use a default sites file if you have one locally, or you specify a given sites file to tailor where Swift should run. But here we're just running locally, and the Swift script actually writes its output into a temp directory, and you can sort of follow this along from the tutorial. So this is kind of a basic hello world script. I'm just going to jump over to a script that's a little more interesting and walk through that. So we'll work on a script here that the context of this little tutorial basically uses these sort of mock science applications to try to act as a stand-in for basically your application here. So this is the sort of the common canonical example of running a large number of simulations and then basically summarizing their results with some kind of analysis script. And we've tried to really strip all the the complexities of the science side out of this, just so we can focus on the essence of the scripting side. So this application here, as the tutorial will walk you through, uses the for each construct to run n sim simulations. It uses this construct here, which is basically Swift's equivalent of argc and argv, to pull parameters off of the Swift invocation command line, and uses mapper constructs to construct the file names that Swift should be, in this case, writing to. So we'll be creating one output file per simulation here. So basically, again, we're running this locally. So you say Swift p6.swift. And it's basically just running here on the local login host. And it just produces output files here. So you see that the produced a average, and this little mock app simulation program is really just a random number generator that has a bunch of different arguments that we can control its patterns to basically teach the concepts of how you pass different arguments in and out of a science app, and you can explore this a little further. So for example, if you were, let's see, and again, running locally, it's using this site definition. There's a throttle here that basically limits the number of jobs that'll run simultaneously, so we can edit that, bump it up, say to run, say, 20 apps locally. And then we can also tell the program, let's see, so I'll clean up the logs that were produced. And let's see, so we'll just run the program again and cat p6. So it has nsim that says how many args to, how many instances of simulation to run, steps to say, how many time steps each one should use. So we'll basically do this swift p6 dot swift dash nsim equal 100 dash steps equals 3. So it's going to run like just 3 seconds per simulation. And so now we should see a greater degree of parallelism in the program. So it's probably actually doing a little more file I/O, but you can see the number of concurrent jobs climbing up to 20, and it'll just crank through the 100 jobs in the same way. Okay, so next we're going to go over and try the same thing on cloud resources. So this is what we've done here is created 3 cloud hosts in EC2. Here's their IP addresses, and we've set up SSH so we can, let's see, okay, so we can SSH to any of these nodes. Okay. And so you can actually get to these nodes, and we'll basically try to have some kind of mechanism that allows anybody to test on some low-cost cloud resources. So at the moment these resources are up. So if you follow the cloud section, you actually should be able to pretty much replicate what I'm showing you here. I've already started a cloud service. So I have running here both an SSH agent that gives me passwordless access to my cloud resources, and a service here that is actually a persistent Swift service that has put Swift agents on every cloud node and lets Swift rapidly send work to those nodes. So now I'm going to be running, let's see, we'll have a different, a few Swift programs here. So I think I'm going to np8.swift. Okay, so I'll be running this program here. So now that we're shifting to the cloud, we're actually going to take one other step in Swift programming. We are going to send the actual scripts to the cloud nodes. So the simulation scripts that we're running is simulate.sh and stats.sh. Let's see here. I think I have a different version of this here somewhere. Let's see. I think I lost an edit here that I had made for my demo. Give me a moment here to. Well, I guess this should be okay. So I have an apps file. Okay. So in this, this is actually correct. In this script, we're actually going to be sending the programs that we're running, these mock simulation programs, as data to the application. So this is going to a useful technique when you're running in a cloud with no shared file system or no pre-installation of your application code. And similarly, in the open science grid context, same kind of techniques apply. Okay, so now we're going to again use sites.xml. Okay, so now we're using a sites file that points to our persistent service that is actually connected to our cloud nodes. We're going to be sending 8 jobs per node, and we're going to be sending, if we look at our apps file, we're going to be running the actual simulations on the cloud in this persistent coaster app definition. At the summary, we're going to run locally instead of, so we're going to send a data file to each cloud node, get a result back, and then summarize locally. So Swift, it's p8.swift. We'll just run with the defaults, assuming I haven't broken anything here. Okay, so now we ran those 10 jobs out in the cloud. And let's see. Here it goes. So /site count will give me a site count of all the jobs total that I've run in the cloud to date, so we can see how the jobs from my previous runs were distributed over this. So now here we'll say -n sim equals 200 and send 200 jobs out to the cloud. So now you can see Swift is routing jobs to sites, moving inputs to the sites, bringing output back from the sites, sort of doing a little more I/O than computation because my runtime here is extremely short. And so now it finished my 200 jobs, and I can say site count and see that, again, my jobs were fairly evenly distributed over those nodes. Okay, so now I'm going to go and use those same techniques to talk to UC3. So this is the University of Chicago Computing Cooperative. That's a model for architecture for campus grids. And I'm sure you've heard a lot about it in this forum. So let's see, I'm going to go over to part 08. Okay, so clean up my previous runs here. Okay, so here I've got my, let's see, I've got an input file here called bias.data. That's just basically a little, parameter I pass to offset the numbers I'm generating, just as a model of passing parameters. My apps file here is pointing just, everything is going to run in UC3 in this case. -np8.swift. So my script is the same. I've changed it a little bit here to be sending the application programs I got just from a different directory. I think that's the only change I made here. So I have basically a little local pointer to my application bin directory. Again, everything here is kind of like a tutorial mock-up of kind of real-life situations, not, simplifies a lot of the real complexities that occur with, big complex apps, but still is meaningful here. Okay, so let's see. So just say Swift p8.swift and use all the defaults. And what I should be seeing now is jobs being submitted into So here I've submitted several jobs into UC3's submit host, and this will take a little while to get started. Actually, they're starting already. Actually, they finished. Okay, so let's start a bigger run. So we'll say -nsim. We'll use these arguments here on the command line. So nsim equals 200 dash steps. So we'll let each job run for, say, 10 seconds instead of instantly. We'll say dash range equals 1,000,000, and we'll say, you know, each simulation should return equal 20 numbers. Okay. And while that's running, show you the sites file for this. So notice in this sites file, we have the ability to pass args through to Condor, where we can specify Condor expressions to route our jobs to different subsets of UC3. I guess in this case, we're using this expression right here, which is routing it just to what's called the seeder nodes, the local UChicago nodes of UC3. So here the jobs are running there. Wilde. So they're basically running. So Swift is basically spreading its load of 200 jobs out over pilot jobs, essentially, that it has placed into all of these workers. And again, this particular Swift script is set so that it's moving the application out to the nodes so that we can basically run with no preparation, no shared file system, etc. So if you have a modest, a fairly simple app with, that can be basically just untarred and run, or untarred and built and run, this technique basically, gives you the, easy ability to just, get running on a, fairly diverse set of resources. Okay, so I'm going to, let's see, I'll just wrap up here with just one brief view of, some other capabilities on slides. I want to sort of, the other context in which Swift can run is to basically now take advantage of many campus resources. So you can, like for example, on UChicago, where we have a local Cray system, the UC3 cooperative facility that is basically a gateway into both local, shared tier 2, Atlas tier 2, and OSG VO nodes, as well as campus nodes. We can basically treat each of these pools of resources as a site, and Swift can route jobs across all of them. So basically, you can put the same kind of site configurations I've showed. You can have several of them in one sites file, and then Swift will basically on demand use the agents that start up as it spreads its pilot jobs over those resources, and take advantage of that fairly heterogeneous collection of resources. But to the scientist, it's basically one logical script that contains your science logic. So what the scientist pretty much thinks in terms of is this kind of logical script that really has no location-specific details in it, and all the location-specific details are in config files like this that config files like this that are pretty much designed once by a site administrator, or a site administrator working with Swift developers or Swift users, and then pretty much used orthogonally to the science scripting logic in the in the user Swift scripts. Okay, so I'm going to stop here. What we're going to try to do is get this demo or this web page that you have the URL for in a shape that you can all try it. And again, as we're heading toward the availability of the OSG Connect facility, I think that'll give us a much broader ability to let a wide swath of people, try this kind of technique, based on these, similar tutorial materials. Okay, so I'm going to stop there and be delighted to take any questions.
Thank you, Mike.
Mike, can you hear me? This is Rob.
Yeah, I can. Hi, Rob.
Okay, so for the pool, so in the sites.xml you have a config file, and in this example you have showing right now, this is for what you call the UC3 pool.
Yes.
Okay, so there are attributes there associated with it and so on. If you were to, do you have the analog of this for what you call OSG, and how
OSG
at the moment anyway?
OSG would be defined, let's see, right here. Okay.
Okay. So
if I wanted to enable OSG, for example, within this one pool, Rob, we could use UC3's routing mechanisms through Condor to give it any of these Condor expressions or put them all together. So in other words, we could define one pool per UC3 flocking destination, or we could define, in this case, like all of UC3 as one destination and let the jobs go wherever UC3 will route them, UC3 and Condor. Okay, so this, the ability to have that flexibility depends on that it requires that you use Swift's location-independent data transport. On the other hand, if you were to use Swift's interface to, say, grid FTP, then we would have to define, one pool per destination. Okay.
Okay.
So,
all right.
Does that make sense?
That makes sense. So I think for the Duke workshop, we are at the moment anyway. We are thinking of a limited number of, in this language would be called pools. So we'll be flocking jobs from the OSG Connect submit host out to the OSG Exceed VO front end. That would be one resource. Because we are going to have a peak demand, during this workshop. We're going to add additional resources that you can get to from the login host. So we will add cloud resources, and so there'll be an Amazon pool, and then there will be we will also have it set up so it will go to UC3. So at the minimum, there would be going to the UC3 campus grid, to the OSG, and then which would be via the OSG Exceed VO front end and gliding WMS, and then Amazon. So that's what we're thinking currently in terms of target resources.
Right, and it'll be exciting to play with that because we'll be able to configure that from the Swift side in a variety of ways. And basically the two distinctions are Swift thinks of it as one pool, and OSG Connect routes pilot jobs for us, and wherever our pilot jobs start, we send work. That would be where we don't discriminate in terms of how we set the data or whether the apps are installed or not and things like that. In other words, if we have that kind of complete generality, we can do that. On the other hand, if we have various differences, like we want to segregate subsets of those OSG Connect resources into separate pools, we can also do that.